developing for the past 15 years, which they're just preparing to open source and make available, all related to the Internet of Things. And it turns
That's
out
even faster than your grad students finish a project, isn't it?
Well, I think it's been finished for a long time. The question is when to open it.
That's right.
Yeah, grad student 15 years doesn't fun. Not for that. And they're right now in the process of opening it up, and this is, I think, one of the first times in which it's going to be presented. And so, without further ado, I'd like to welcome scientists.
Thank you very much. It is great to be here. I'm really excited about the presentation. I was saying earlier that the quality of this presentation is really going to depend more on you than on me, because it's the questions that really make it. I'm going to try to blast through these slides, and then maybe all of your questions will be go back to slide 5 so that I can see what it really said. But first off, a little introduction to Panasonic. When you think Panasonic, what do you think? Lots of cheat sheet up here, right? What do you think? TVs? Okay. Okay. Would it surprise you to know that in North America, more than half of our revenue is actually B2B? If you fly on a jet, chances are probably 80% that Panasonic makes the entertainment system that you use. In addition, Panasonic instruments about, I think, 1,500 airliners in the United States collecting weather data. We have, I believe, the largest private cloud in the world churning on this weather data. If you go to AccuWeather, it's actually data coming from Panasonic weather systems. Okay, anybody been to the Derby, been to the racetrack? That is a 20,000-foot screen, largest screen, I believe, still in the world. And yeah, those are people, the little pixels down at the bottom.
What technology is this display, Brian?
That's LED.
How many LEDs in a 20,000 square foot thing?
I don't know how many billions. I mean, a lot, a lot. I'm not sure what the dot pitch is on that one, but there are lots of little panels. You drive a car, a nice car, then it's probably going to be a Panasonic infotainment system. So we deal with a lot of data. What I'm going to do today is actually a preview of coming attractions. As Philip mentioned, this is, I believe, the first kind of in the wild presentation of our technology. It's going to be officially announced in about 3 weeks at Embedded Linux. So the technology that I'm going to talk about is called DOF, which stands for Distributed Object Framework. And the open source project will be OpenDOF. We're planning over the next, I'd say, 6 months, releasing on the order of 400,000 lines of code, which is basically our entire IoT infrastructure. So, as I said, I'm going to blast through some stuff here. I want you to feel free to interrupt me, though. We'll take questions at the end as well, but if there's something that you want me to talk in more detail about, let me know. So a couple of terms that I'm going to use a lot, and these are terms that most of you are going to be familiar with, but we twist the definitions just a little bit. The first is object. I'm going to use that as a distributed set of uniquely identified capabilities. Don't think a Java object, that's too limited. Think of a distributed thing that exists in multiple places. Interface is going to be a defined set of capabilities, and that could be properties, methods, events, exceptions, and it's bound to a unique identifier as well. This you can think of more like a Java interface. It's implemented somewhere on a real piece of compute equipment. Oh, sorry, jumped ahead. Identity. We're going to talk a little bit about security. And so an identity is a unique persona associated with a secret or secrets and a set of permissions. That's going to be the foundation for our security model. And then finally, a domain, which is a centralized database of identities. So you can think of that as both the identity itself as well as all of the permissions and all of the secrets. I'll get into this a little bit later, but we centralize this information rather than distribute it. Everything else we distribute. Okay, so a little bit more about object identifiers. Object identifiers in our architecture are globally unique, but there's no registration required. We do this by actually registering the prefix for each object identifier and then tacking on whatever unique data you have. So if you have a MAC address, I can make it an OID. You have an email address, I can make it an OID. You have any unique piece of information, a product serial number, anything that you have access to that is locally unique, I can tack a header on and make it globally unique. Question? Just a sigh. Okay. Here's some examples. So that's me as an object identifier. I can use my email address. The bottom is actually my laptop, so that's its MAC address. Again, any piece of unique information, I can tack a header and make it globally unique. We do like these to be stable, though, because we're going to end up granting permissions based on these object identifiers. So coming up and randomly assigning yourself a GUID doesn't do much good. It's guaranteed random, which means that it is guaranteed to have no assigned permissions. So pretty worthless object. We want it to always come up with the same identity. Sorry, yeah. So 3 is the header. It's the assigned, the question was, what's the 3? That would be the assigned class for an email address. 2 would be the assigned class for a MAC address. So we've got a great big registry of these, and if a company came to us and said, hey, I've got a product serial number for my toaster, then we can give them a number, and now their toasters have globally unique identifiers.
What is the 060?
Okay, excellent. So the question is, what's the 06? In the wire format, which this is, it's going to be class, and it's a compressed class. We have more than 255. Length of the data, and then the data itself. Excellent. Keep the questions coming. Okay. Next is an interface identifier. Again, for an interface identifier, think of a Java interface. So this is defined functionality. Here, we are globally unique through registration. There's a reason for that. We want interoperability. And the way that you get interoperability is by registering what your capabilities are. Rather than standardize these, we're not a standardization body, we just register them. And so you would come to us, you'd say, hey, I've got this nifty interface, here's the definition, you can give it to us in XML. We'll publish it, we'll assign you a unique identifier. We actually have a number of different registries, only 4 of them are assigned. So if you're a big company and you want your own registry to make your own assignments, we can give you one of those registry IDs, and then you can handle the assignment on your own. These are very small, so 5-byte maximum. So this time I'll anticipate the question. The 1 in this case is the registry number left shifted 2 bits plus a length flag. And so that means that the length is actually in that first byte, and then the 2nd, 3rd, 4th bytes are going to be the actual number that's assigned. These are real. Well, no, that one's not. That one's real. I'll use it later on. That's a status interface. OK, error, warn. The last one I just made up. Okay, and then the last thing is an item identifier. Within these interfaces, I've got to define different things. I need events, I need properties, I need methods. And so we assign each one of those a locally unique ID. So these are very small numbers, up to 2 to the 15 possible. One of the things that is a little bit unique in our system is that in our interface definitions, we deal with both the syntax. That means this is a Boolean, or this is a method that takes 2 Booleans. We also include semantic information. So in the Java world, you could think of an interface that says on, off. and it is a Boolean, right? Well, that's good for syntax, but I've got lots of things that I can turn on and off, a coffee pot, a light, a projector. And if I really want to use discovery on things that I can turn on and off, and I'm a wall switch, I don't want to be turning on and off the projector or the coffee pot. I want lights. And so on-off for a light has a different semantic meaning than on-off for the coffee pot or on-off for the projector. Okay, so we put all of these things together into what's called a binding. A binding is an object identifier plus an interface identifier. And in combination with an item identifier, so those three quantities together, I can uniquely identify any piece of functionality anywhere in our network. So that is the object, the interface, and the item. Doesn't matter where the object is. It doesn't matter how the interfaces are distributed. I may have an interface that's actually implemented on the device, and I may have an interface on the same object that's in the cloud. That's not a problem. That's why I say you have to think of object in a much broader sense than just something like a Java class. Operations, if I want to act on that data, set it, get it, retrieve it, I'm going to require a binding plus an item ID. And those, you can imagine, can be large. I can have an object ID that's really big. So if I have context on the wire, then I'm allowed to shorten that, and I can use an alias. So that's just a negotiated, very small number that represents that much larger quantity. So as an example, here is item 1, which happens to be the status property of the status interface of my computer. So the first one is the item, then I've got my interface, and I've got my object identifier. If I've got some context, and let's say that I had negotiated the alias 8, then I can represent that in 2 bytes on the wire. If I don't, then I've got to pass all of that information. So again, that's globally unique. Anywhere on our network, that identification is going to mean exactly the same thing. It's going to go to my computer and get the status. Okay. That's the extent of our object model. Really simple. You got 3 things, you know everything. So how do we take those 3 things and make them secure? Well, the first, I'll talk about domains. So our system is distributed as far as the object model. The objects, the interface implementations can be anywhere in the network. But you can't fully distribute security. I can't give every device on the network my secret, because then he could be me. So we swing the pendulum entirely the opposite direction, and we centralize all of the security information. That includes all of the identities. So that is the object identifier that means me. My secret, that could be a shared key, it could be a password. And all of the permissions that have been granted to me.
Centralized, do you mean over the entire world, or for a particular principle? Or like, is there some big database in the sky that contains the entire Internet of Things?
Good question. Let me see if I can echo that back. So is there one massive authoritative database in the sky for the billions of devices in the Internet of Things? The answer is no. That's the right answer. What we do is we split it up into a domain. So in any security domain, any set of actors that are actually going to interoperate, yes, then it's centralized. But I may have millions of domains. As an example, if I'm a residential system, I may have a domain for my house. Well, there are 100 million domains right there. It's very rare for my house to talk to my neighbor's house. There are use cases, but it's fairly rare. And so there's really no reason that my domain and his domain ever have to come in contact. So while they're centralized, they're not centralized all in the cloud.
Devices being multiple domains.
Sure. Yeah. If sorry, the question was, could a device be in multiple domains? As long as he has a unique secret. We do not like sharing secrets between domains. That'd be a security violation. But I can have as many secrets as I want.
It's like a shared security camera for an apartment complex.
Yes. So yeah, a shared camera for a security complex could be in its own domain, something that is the complex itself.
Each house has to be able to access it.
Yeah. In that case, yeah, maybe the control panel in the house would have a secret for its participation in the condominium, the apartment, with very, very restricted permissions, yeah.
So, sorry, then it is the case, though, that devices can't talk cross-domain.
Devices are prohibited from communicating cross-domain. However, we do have the sense of what we call a security bridge, which is at the application layer, I can configure certain cross-domain communication. Because the application obviously can do whatever it wants, right? I can read a value here and set it over here in a different domain.
If you have access.
If I have credentials in both domains.
Do you have an example?
At least in some of the Japanese systems, it's very, very common for the LAN environment to actually be unsecured. We treat unsecured as a special domain that just doesn't check credentials. And yet, I may gather some data on that and want to send it into the cloud. The cloud certainly is secure. And so that would be an application layer function where I'd read some unsecured data and send it securely into the cloud. Another question?
What happens, let's say an organization or corporation wants to implement IoT for their own purposes?
Mm-hmm.
The building or across the world, there is different users, different security that needs to be implemented. Would the system be ideal for them to set an infrastructure?
Sure.
Have different roles, different users that can access the same kind of
Yes.
systems, but with different permissions.
So the question was a little bit long, but yeah, could you use this kind of system in kind of a federated or an intranet, a company environment? Certainly. We don't have to run this domain. The company can run it on their own. In fact, in Singapore, we run a set of systems where we can either run it in the cloud or they can install everything local. Some universities don't like sharing information with the cloud, and they just run the domain local versus running it in the cloud. Great questions. Any others? Okay. So with that security model, each interaction in our system typically requires 2 permissions. That sounds a little bit odd, but you can think of it this way. If I wanted to read a file off of a hard drive, everybody is familiar. I log in, I get my UID, my GID. I've got some permissions. It's usually read, write, execute, and that gives me access to that file. We don't often think of the hard drive having permission to contain the file, but that's the way that we model it. So if that hard drive didn't have permission to have the file, then I will be blocked from reading the file, not because I don't have rights, but because the drive itself doesn't have rights. You can think of that as permission for the request and permission for the response. And so when I talk about an identity and I'm going to grant him permissions, I can grant him permissions in one of 3 roles. One, as a requester, you have permission to read this value. One, as a provider, you have permission to provide this value. And if I combine the 2, I've essentially just created a gateway, meaning that one thing is a requester to a provider who is also a requester who links to another provider. And you can see that that chains to an arbitrary length. I can put as many gateways as I want.
You separate, read and write? Say I have the
Yeah.
permissions
So question is the different permissions. So we have read, write, execute, and provide. We also have an extensible permission model. So if you want to model some different, unique kind of permission, then you just register it with us, define it in your code, and then we'll enforce it for you. Okay, other questions? Yeah?
Can you give a specific example in the IoT domain, how this model is being used?
A specific example in the IoT domain. Trying to think of the best example. Sure. Okay, so we would put a gateway in a convenience store in Japan. That gateway has access to a bunch of different devices that are in the store. It's gathering data, it's pushing it into the cloud. But maybe they want to go in and tweak one of those pieces of equipment, and so they may have a control application. The control application would have the requester permission. The gateway would have both requester and provider, and the device would have provider. So I'm essentially chaining that access through the gateway. As the requester, as the client app, I look at the gateway and see a device. I don't see a gateway. And the gateway sees me as a requester, sees the actual device as the provider, and he's just passing information through. Does that make sense? Other questions?
Those kinds of bridging circumstances, do you have end-to-end? I mean, so you can imagine this way: the gateway could be rewriting the requests, or could be what are the integrity and confidentiality guarantees you get in these bridging cases?
So because of the way that our system is distributed, nobody knows until the actual path is established where the path is going to go. And we also allow redundancy, so I can have a provider in actually 2 places, and I'll use the closest one. Because of that, at the lowest level, we can't do end-to-end. But I can lock onto a provider, and at that point, I can open an end-to-end encryption session. So at that point, I'm not encrypting everything, I'm encrypting the data, but that's the way to get end-to-end. Okay?
Is that fully end-to-end to the device?
It'd be fully end-to-end until it left our system. So for example, if the device is speaking some RS-232 protocol unencrypted, I can't get all the way to the end.
But if I've got one of these application bridges,
It would go through the bridge, yeah.
go through the bridge encrypted.
The payload would be encrypted and go through the bridge. Because the bridge never has to look inside the payload. He doesn't care what it is. Okay, so this is my one kind of encryption-based slide. You can look this up. It's called kryptonite. It's very, very similar to Kerberos. You can see the A and B, so I've got Alice and Bob. Each has their identity. They each come up with a nonce. And then there's a whole bunch of encryption. Or actually, there's only a little bit of encryption here. These are MACs. So this is really, really pretty simple stuff. This is going to do a key distribution. The key is going to be generated up here and actually passed back, XOR'd in with this encrypted payload. When we first analyzed this, we thought, oh, this is great. It's very, very simple. I mean, you can implement this with no big num, nothing. I mean, very, very simple. You need HMAC, and you need something like AES. But what we found was that nowhere in here is the definition of this nonce really specified. The nonce has to be unique, but it doesn't have to be small. And anything that is in the nonce ends up being mutually authenticated, meaning that both Alice and Bob trust the value of that nonce. And the domain controller actually had access to the nonce. In a similar way, the domain controller can pass arbitrary information out, and as long as he puts it in this MAC, it's going to be mutually trusted as well. And so if you look at these different spots, we can actually put permission requests into the nonce. And what that means is that the domain controller will get the permission, the request, can actually check the granted permissions, generate a response, and both Alice and Bob will trust that response because it's tied to the key. If either one of them tries to falsify anything, they won't agree on the key. And if they, even if, well, they could always get together and collude. But anything that the domain says regarding the permissions is going to also be trusted.
Sorry, maybe I missed it, but could you maybe describe, like, at a high level what's going on here?
Oh, at a high level. So Alice comes up and says, I want to talk to Bob. Comes up with a unique nonce, something that Alice hasn't used before. Identifies herself as Alice. It can be random. What will happen is if there's a collision, then you may open yourself up to a replay. So it's good that it's large and either sequential or random.
How does B know what NA is?
So Alice is going to pass this over the wire to Bob. Bob is going to generate his own nonce and identity and pass all of that up to the domain. The domain is going to generate both a MAC of all of these quantities and then encrypts it with the private key of Alice or Bob, and then XORs it with the distributed shared key, which the domain generates. So that's just a big random key. Bob is going to take this quantity, regenerate it, make sure that the MAC actually matches, encrypt it with his key, and XOR it with this. And that's going to give him the distributed shared key. And then is going to pass through this second group over here. And I was also going to pass a proof that he actually was able to get the shared key correctly. And then Alice is going to send a proof back. So at the end of the day, they both know KAB. They've both verified that what they passed in was used to actually generate the key. And they know each other's identities as vetted by the domain.
How does it prevent somebody listening this communication?
Well, they can listen all they want. They will see everything, but unless they happen to know the secret of A or the secret of B, it's all just a bunch of hashes.
Sorry, so the goal here is that A and the domain and B and the domain share some secret already, or the domain
Yes.
knows their public keys. And A and B have not interacted before, and they want to communicate encrypted.
Correct.
And so they're using the domain to generate some shared secret key. Okay.
Yes. I won't try to summarize that, but yes, that was an accurate summary of what we do. Okay, other questions? What's that?
Why do you need that Kerberos doesn't already provide?
Okay, so what is it here that Kerberos doesn't provide? This is a little bit simpler as far as flows from Kerberos. And we were able to make these modifications easily to add in the permission checking. But you're right, it's very, very similar to Kerberos. Okay, other questions? Okay, I want to leave time for Q&A. So I'm going to blast through these API slides so fast that there's no way that anybody's going to follow it. But it's cool, trust me. So at a very, very high level, we wanted an API which hides as much of the underlying protocol stuff as possible. The side effect of that is that a user of our API really doesn't have much control over what's happening on the wire. We try to do the best we can, but you can't control every packet. It's also written for the most general case. And the most general case is not always the most scalable case. We have examples of tens of thousands of connections. We have requests for systems supporting hundreds of thousands up to millions of connections, simultaneous connections. So to get there, we're going to need to do some work. I'll come back to that. And just a general comment, APIs are hard. I mean, just designing APIs is hard. I've been doing it for 30 years. They never please everybody. So they're not going to please everybody here. Still, I think they're pretty cool. So this is an example of instantiating a DOF. The DOF is kind of the main framework entity in our system. So basically, I've got some credential information. I create a DOF. We use the Java Builder paradigm quite a bit for future proofing. And at the end, I create a new DOF, and I create two systems. Systems in our API are the interaction points between the application and the DOF. And so pictures are always better. So what I've got is a domain up here, call it the green domain. I've got my user identity, my set of permissions. I created two systems, and I attached my identity to those two systems. So they're now secure. Anything that happens in my application that goes through this system is going to be permission checked. It's going to be tagged as me. OK, so from there, I'm going to instantiate an object. The object is our main kind of focal point for providing both interfaces and also using them. And so I'm going to create one called a requester and one called a provider. And if you've got excellent memories, that's the MAC address of my computer. Don't abuse that knowledge. OK, so what this did is it took my existing systems and tacked on these objects. An object, really, I don't define whether it's a provider or a requester. It could be both. It's all in how you use it. OK, so the next thing I'm going to do is actually provide some functionality. I'm going to do this on my provider. So I'm saying begin provide. And all the magic is actually in here. That is my definition. It's the interface identifier. It's the list of all the methods and properties. It's a great big Java class that I created. And I'm also going to provide a listener. And that's real code. I don't have to do anything more. If I use one of my default providers, then all I have to do is tell it how to respond to a GET. OK, so what do I do on the requester side? Well, over here, in order to find an object, I'm going to express interest. Interest is a real network operation. It's going to send packets out through the entire system, finding objects that match what I want. And then on the system, I'm actually going to do a query. You can think of this as a database query. I can give it the interfaces, the objects that I'm interested in, and I give it a callback. Now, this is not real code. You see ... The implementation of those are really mostly one-liners. This is a local request. It doesn't actually do anything on the network. And so going back to our picture, what I've got is a query listener attached over here, an interest that's now flooding through the network, finding these providers, and then this guy is now tagged. He's really a provider of some functionality. Told you I'm going to go fast.
So you talked about the network, right? Network is a network of sensors, a network of gateways.
Could be anything. Yeah. Yes. I'll get to that. OK, so now I'm going to interact with a provider. And this is a synchronous call. In fact, everything that I've been showing you, for the most part, is synchronous. I can do this asynchronous as well. I'm going to do a get. I'm going to tell it the item identifier I want, give it a timeout. I'm going to get a result. I typecast it, and I'm done. The interactions that I can do are property get set. I can do subscriptions for push notifications. I can invoke methods, and I can register for events. Events are just asynchronous things that occur. OK, so now going back to all of our security discussion, I'm going to track this operation through. So it starts out at the application. It moves to the system when I make the call. And the system internally is now going to go through all of that key exchange, is going to validate that what I'm requesting is approved or possible based on the permissions that I've been granted. If it passes, it's now a green operation, right? It's been vetted. It's going to move through the DOF to whatever provider was chosen. Provider is going to generate a response, but that response is now at the application layer. It's not vetted yet. Goes back into the system. The providing system is now going to check that it matches the permission. It does in this example. It's green, and so now my green response makes it all the way back to my requester.
So suppose that the response wasn't vetted. Would I then encounter a timeout?
You get a timeout. It depends on which side. If the requester can actually validate that it's not possible, then you'll get a permission exception because the requester knows. But if the requester sends it out into the wild, he doesn't know. Right? It could be a DOS attack. It could be anything preventing that response from coming, so he'll get a timeout. Good question that I forgot to repeat.
The provider does not come back with a permission exception.
No, he won't.
It's just not there.
Yep, he's gone.
What about in your expressing interest, essentially your pub sub?
Mm-hmm.
Is that permission or?
Yes. Yeah, so the question is interest governed by permissions? And the answer is yes. Usually it's an inherited permission. What I mean, if I have permission to provide, I'm automatically a provider. If I have permission to request, I'm automatically a requester. But those are separate permissions that I can grant. So I could allow only discovery, and you can't do anything else.
So does that mean that the domain has to be online whenever you want to interact?
Ooh, very good question. And yes, the answer is yes. So that's the one point where you could say that we've got a single point of failure. Although, we don't necessarily say that there's only one of these. So you can make them redundant. You have to keep them synchronized, but.
Yeah, but like if I want to open my car in the middle of the desert and there's no 3G.
Yeah, you're screwed. Don't lock your keys in the car. Don't lock your car.
But so when these operations are vetted, can you then cache those?
Yes.
Right, so.
Oh, yes. Yes, and so, I mean, I haven't gotten into a whole.
If you opened it outside your desk.
Yes, then you could get away with it. We actually do that because otherwise all the key exchanges really get in the way of performance. Yeah, and actually that's a lot of what we would do. So the domain for your car may actually be in your car, and then it's always online.
But the domains don't federate, and so then I'm restricted with the communications that I can have.
They do federate. So I didn't talk about this much, but we run a demonstration where I actually have my domain, all of my identities, my secrets, my passwords on a residential gateway connected to our cloud. And I can connect a client to our cloud using my home credentials. And the cloud will actually find my domain, vet everything, and allow me to connect through the cloud, even though the cloud has absolutely no clue what my secret is. So in that way, it can federate.
So are you going to talk about how permissions actually get established? So we were talking about access to your laptop.
Mm-hmm.
Presumably, you don't just randomly allow anybody on the Panasonic network to talk to your laptop.
No, so they would, one, need to be in the domain of my laptop, and two, I would have had to grant them some kind of permission to access that.
So you have to do that for each individual requester?
Yes, I have to do that for each individual requester. Now, that isn't to say that my domain can't implement some kind of higher level meta language that actually creates permissions on request. But it means that, in effect, yes, there has to be an explicit grant to each person. So it doesn't have to be that difficult. Let's see, over here.
Yeah, Brian, have you compared to a blockchain and the Ethereum peer-to-peer model, public ledger, right? That's everything kind of like a database, not centralized.
So typically, our domains are, we use Cassandra. So we actually do distribute all of the information. I don't think that we've compared the ones that you mentioned. Oh,
Like a blockchain, right? Like
yeah, no.
Bitcoin, you can-
Yeah, no, we haven't looked at that. That would be a great thing to look at, though. Other questions? Okay, I wanted to leave some time for Q&A. So everything that I just showed you was essentially on one computer. So what I'm going to do now is I'm going to create a server. All of our servers are done through plugins. So you can add any transport that you want. Those 4 lines are actually going to start up a TCP/IP server. And because I tacked in the security, it's now a secure server. And those 4 lines will actually open up a secure connection. And so graphically what happens is this. This is my original single DOF system. And I split them apart and I open a secure connection between them. Now, there are a couple of things to notice. One, the server and the connection logically are inside the DOF. What that means is they are totally transparent to the application. I did not change a line of application code to make this work. All I had to do was split the program in half and put the requester in one program, the provider in another, and add the code to open the connection. It doesn't matter how complex this topology is. I showed a really easy topology. It doesn't matter how many links I go through. I'd have 2 gateways going through a cloud. I could have 2 clouds with 2 gateways. It really doesn't matter. As long as there is a secure path between the requester and the provider with the appropriate permissions, they'll find each other and work. Okay, believe it or not. What's next? So I mentioned this earlier, scalability. Right now we scale to tens of thousands of connections. We know that we need ultimately to scale to millions. That turns into a large distributed routing problem for our discovery. We've got a couple of ideas on how to resolve that, but that's an active area of research for us. And of course, whatever we come up with has to be able to enforce our security model as well. Optimizations. We actually handle failover of connections. So if I'm a gateway and I have 2 connections and one of them drops, the system will actually reparent all outstanding operations to the other connection. So essentially, you won't know that that connection went down. Things just keep working. That actually is a difficult problem. A lot of state that has to be maintained, and handling that is certainly an area of research. And that ties into minimizing state updates. You know, if I've got 1 million devices or 100 million devices, does every node in the network have to learn about every one of those devices? Well, to do really fast discovery, yeah. But again, we want that optimized. So years of research.
When you say scalability, tens of thousands to support today, is that a single DOF you're talking about?
Yeah, tens of thousands onto a single DOF.
So
Yeah.
you could have,
But because of the way that we handle the routing, it actually is going to grow, right? As I mesh things together, I keep track of the entire mesh topology, which ultimately is not going to scale.
you can't, DOFs, you can't put them in the hierarchy.
I can divide them by security. So if I know how the domains are partitioned, then I can restrict the information flow. But again, that causes problems for when I open a connection, who do I connect to if they're not all equivalent? Other questions? Yeah? Oh my. So we actually do a lot with batteries and energy. And we have a 1 megawatt battery, lithium ion battery system in Japan. It's actually at a factory off in the boonies somewhere. And we were trying to do a demonstration. We wanted to control this lithium ion battery system. So we actually hooked it to a control signal coming out of New Jersey. PJM, they're an energy company back there. And they were sending us a signal every second saying, you know, send energy in, send energy out. We networked that to the factory in Japan. And with about a half-second latency, we were controlling a megawatt battery system, telling it to discharge, charge, discharge, charge. That was fun. Other questions? Yeah. That's a good question. So the question was, what are the license terms going to be? We are going to be working very closely with the All-Seen Alliance. We're looking at actually their license, which is the most open license that I think I've ever seen. In combination with that, and again in the spirit of pre-announcing, Panasonic will be announcing patent non-assertion on any claim required to implement this technology. There is. So there is the Open Interconnect Consortium, and we'll happily play with them as well. Their specifications are not open. Our specifications will be open. So along with the open source, we're moving to open specification. So every bit of every byte in our stack will be specified. So you could white box an implementation if you wanted. I can certainly answer that. But again, also in the spirit of forthcoming announcements, I would say middle of year, maybe third quarter, Panasonic will be announcing a set of cloud services that are compatible with all of this technology. So that's ultimately our play. We want to either bridge your devices, we want to provide reflash services, security services, connectivity services. And that won't be free. But if you want to do it on your own, more power to you. Okay. We're actually, so our cloud system is already running. It's been internal to Panasonic, running production loads for a little over a year. It's running on Amazon. We'll leave it on Amazon. How much is this in production? So all of the libraries are implemented in Java, C#, and C. We have 2 versions in C. One of them, non-secure, is about 15K of code. Secure is a little under 50K. Java, the jar is a little over a meg. C, it's not C++, it's straight C. I think it's about 700K. Those are all Release 6, so they've been under development for the better part of 10 years. The security has all been vetted externally. It's also been the target of pen testing inside Panasonic for about a year. So we're pretty confident in the implementation. The cloud system is running today.
To what extent are you shipping devices on this?
Most of today's, so the question was, how many devices are we shipping?
Yeah, in orders of magnitude.
Yeah, orders of magnitude, tens. The reason I say that is for most of what Panasonic is using this for, it's B2B. So, for example, we're running, I think, about 140 solar sites throughout the United States. But they all go through concentrators, and so there aren't that many devices. I think Singapore is probably the largest. They've run up to about 1,000 devices with their application. And then we've got 2 projects that are now talking in the hundreds of thousands.
So we've got about 1 more minute.
I got 1 more minute.
Yeah. So
Questions count.
Questions afterwards.
Okay.
How do you see this standardization effort playing out over time, given that we have, at least you're going to have OIC,
I'll join.
Scene, right?
Yeah.
Google.
Yep.
And Apple as major players.
So how do I see the IoT market playing out?
Yeah.
I don't believe that there's a Borg out there yet. I think it's going to be a lot more peaceful coexistence. My prediction would be that the importance of gateways is going to be high because no one is actually going to win. And not only is one protocol not going to win, one transport isn't going to win. So that means you're going to have a gateway by default. I think maybe that was my last one. I will hang out here as long as people want to ask me questions. So thank you very much.
Thanks, Brian. That was great.
Thank you for having me.